Hello there. Today I want to show you how you can replicate my aim constraint with a bunch of DG nodes inside the node editor. So first I want to use my standard my aim constraint and see which options I have and what I can do with it. So here I have a scene with a root object, a constraint object which is parented to the root, and the target object on top of that. I want to aim my constraint aim object to the target with its y-axis. So let's see what options I have inside the aim constraint. Let's reset all the options to default one. And I want to change my aim vector to y, change my up vector to z, and I want to use my world up type to vector as a vector, and I will change it to z as well. And let's see what it gives me. So I created my aim constraint here. Now when I move my target, my constraint aim object follows it and aims to the target. And also if I move the root, it will still follow the root and aim to the target object. But unfortunately, I don't have a twist, and my aim object flips when it goes beyond the 90 degrees, beyond the 90 degrees in both directions. So the range is 180 degrees. And let's see what I can do with it and how I can fix it. Let's start with adding object rotation up as a world up type and choose my root as world up object. So if I use these options and apply my constraint, now I can twist my aim object and it would aim to the target. But I would still have the flip. So what I can do with it, I can change it back to vector. Let's delete the constraint. And if I set the world up vector to 0 vector, that would give me a result that I am looking for. Let's apply. And now we can see that we can aim my object freely toward the target. I have my twist and I don't have any flips anymore. So let's reset it back to origin. So yeah, now I don't have any flipping issues, and I still have that twist. And also I can even move my constraint object and it would still aim towards the target. So let's see what we have, what connections we have from our aim object to the aim constraint and from our target as well. So we have a standard parent inverse matrix from our aim object. We have a bunch of stuff that we don't care about because the rotation order would be similar XYZ, and the rotate pivot and rotate pivot and slate are zero vectors, so we don't care about that. And we have to look into here and see that we have the translate, local translate of my target connected to the target translate, and its parent matrix as well. So let's keep it in mind and delete my aim constraint. So let's start building our aim constraint with just nodes. And the heart of my aim constraint would be the axis angle to quaternion node. So basically I need to find the axis of rotation, the angle on which I want to rotate my constraint object, and then plug it into the rotation of the result of axis angle to quaternion into my rotation of my aim object. And to plug it, I need to convert my quaternion into the Euler angles. So we would use what to Euler, connect it, and plug it into the rotation. So now we need to form the axis of rotation and find the angle on which we rotate it. And my root and my target objects, they can live inside the different hierarchies. So if I put them into some groups, so maybe my target would be somewhere here. It is parented to my null one, and my targets, let's say it's parented to null two, so they live inside the different hierarchies. And to compensate for that, let's remove it from graph. To compensate for that, we need to convert our translation into the world space. So basically, first we would need to find the difference between those two objects, the difference vector, the delta vector, and the delta vector should be in the world space, at least at the beginning. So let's put our translation into the world space for the root and for the target. And to do so, we would need to use multiply lie point by matrix node, and we plug the translate, and for the matrix we would use parent matrix for the root, and let's do the same for the target. Come on. So we have both of our translations are in the world space. So now we can find the delta vector by using this plus minus average node, set it to subtract, and let's subtract my uh, my root from my target. The input 0 would be my target world position, and input 1 would be my root world position. So that would give me my world space delta. And now we would need to put my world space delta into the root local space. So we would need to put this delta and transform it into the local space of my root as a vector. So basically that would be something like that. Let's clean it up. And to put my delta vector into the local space of my root, I need to do another vector matrix multiplication. Multiply vector by matrix. And we plug our world space delta into the input, and the matrix would be the root inverse matrix. So now we have the local space delta. Okay, so why do we use these two different point and vector multiplications? And the reason behind it is that when we multiply our vector with a matrix, with our matrix, we do the linear transformation. And when we multiply our point with a matrix, with this matrix, we do the affine transformation. And the difference between linear and affine is that the linear transformation, it just transforms or imply the rotation, scale, and shear. And for the affine transformation, we also add the translation. So TRS and shear as well. So the main difference between point and the vector is this homogeneous coordinate, this fourth component of our vector. We need to use it just to be able to multiply vector and point with a 4x4 matrix. So we need to have the 4-dimensional vector to multiply it with a 4x4 matrix. And the main difference between the vector and the point, that the homogeneous coordinate for the vector is 0, and homogeneous coordinate for the point is always 1. And basically, when we multiply our vector with a matrix, we consider only this 3x3 matrix. And because of the homogeneous coordinate is 0, our translational component of the matrix doesn't have any effect on our vector. So that's why we get the linear transformations. So basically, for the vector, we would have x prime, y prime, and z prime. And for x prime, that would be x times a11 plus y times a21 plus z times a31 plus w times a41, and because of w is 0, we would have a big fat 0 over here. So for y, that be x times a12 plus y times a22 plus c times a32 plus 0. And for z component, we would have the x times a13 plus y times a23 plus c times a33 plus 0 as well. And we can see that we do the dot product between our vector and our matrix columns when we multiply vector by matrix. And we have to say that our Maya transformation matrix, they are row major. So that's why first we have the vector, our vector times the matrix, and we do the dot product between the columns when we multiply a vector by matrix. For the point, when we multiply point by matrix, here we have the w times a for 1, and the w is always 1. So basically we would have a for 1 for x prime, a for 2 for y prime, and a for 3 for z prime, and for w that would be 1, because when we multiply these components, which are 0 for our row major Maya transformation matrix, and this component would be 1. So that's the main difference between point and matrix multiplication and vector matrix multiplication. Let's go back to Maya and continue with our axis angle stuff. So when we transform our world delta into the local space of our root, we need to consider this little offset between my constraint object and my root. So, and to do so, we need to do another subtraction. So here we need to subtract from my local space delta the local position of my aim object. But I would keep it as a constant. So here we have 2 units in y direction. So here we can see it has 2 units in y direction in local space of my root. So now when we have this local space aim delta. We can normalize it. And now I would like to explain how axis angle to quaternion works. So so our quaternion is basically I, J, K, and W floating point components, numbers, just like the vector. But it's very nice to consider our quaternions in terms of axis angle of rotation. So basically we have the axis of rotation and angle on which we rotate. And to build our quaternion with axis angle, so we would have this angle, and this x, y, and z would be our axis. So axis would be the normalized vector x, y, z, and the angle theta would have the range between 0 and pi. And to find our angle based on our delta vector or our local space aim vector, we would need to consider the aiming vector, which is y hat or normalized vector. Basically, in our case, that would be 0, 1, 0. And our delta vector, which should be normalized as well. And the angle would be our cosine of our y dot d. That is our angle theta. And to find the axis, we would need to do the cross product of our y and d hat. In the vector of rotation, basically the axis would have the orientation or direction which we can find by the right hand rule. So first we use our y hat, then we cross it with d hat, and our axis would be negative z in this case, so it would look in this direction. And if we have this vector from the other side, so d would look somewhere into this direction, then our cross product would give us this axis, which is perpendicular to this plane. Okay, let's go back to Maya and do it here. So here we have the normalized aim delta vector. Now we need to find the dot product between our aiming vector, which is y, and the normalized local aim delta. And the cross product for our axis of rotation. The first input would be our y vector, this vector, and the second one would be our aim delta, local space aim delta. And we don't need to normalize it here in Maya because our axis angle to quaternion would do the normalization for us when we plug in our input axis. And now to find the angle, we need to find the arc or a cosine of our dot product. Now when we connect, we can see that our aim vector, aim constraint now works as expected. So basically that's the same as we have for our standard aim constraint in Maya. Everything works exactly the same. And if we want to, we can connect our translate into our aim local space in delta. But please don't do it. It's considered the bad practice when you have the cyclic graph. So here you go. The aim constraint with DG nodes in Maya, or the aim constraint in a nutshell.